Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajmain. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Allahumma la sahla illa ma ja'altahu sahla wa anta taj'alul hazna idza shi'ta sahla. Okay, assalamualaikum and good day to everyone. Okay. So alright, so for this video, I will showing you and teaching you on the chapter 2, which is strain. So from the chapter 1, I believe that you already understand about it. You have learned about the internal loading having 4 different loads, okay, axial, normal, okay, shear, bending, and torsion, okay. And also you learn about stress. There are 2 types of stresses. Number 1 is normal stress, and number 2 is the shear stress. And for this video, I will be teaching you on the chapter 2, which is strain. So you will learn about strain deformation. So you will understand when the body is compressed or tensile, the body will be changed in length. Okay, so the changes in length can be calculated, can be used to calculate strain. Okay, all right. So, oops, why this cannot be moved? What happened? Oh, it is lagging. So I can move my presentation slide. Let me try to fix this one first. Okay, so we move to the next slide. So this is the thing that you will learn for this video. The first one is to define the concept of normal strain, and number 2 is to define the concept of shear strain. So you'll be understanding what is normal and also what is a shear strain. Okay, so it is similar like stress. We having normal and shear stress, and also happen to the strain as well. And the last one is what? To determine normal and shear strain in engineering applications. So you learn the concept of normal and shear strain, and later on you will use that fundamental knowledge, okay, to calculate, to determine normal and shear strain in engineering application, especially in biomedical engineering application. Okay, this is the chapter outline. So of course, deformation and strain is the main topic, main subtopic that you will learn. And we move to the deformation. So if you still remember, during my first lecture, I'm showing a rigid body. Okay, when an external force is applied to the rigid body, and the rigid body somehow will be deformed into a deformable body. Okay, so once the body is deformed, so we can calculate the deformation. Okay, so what is deformation? So deformation is actually a change of body shape and size. Okay, when a force is applied to a body, okay, the body itself will be changed, okay, in terms of its shape and also size. Okay, so you have a 2D body like this one, okay, for example here, and we compress it like this one, for example, and then the body will be change into a deformable body. Let me change the color here. Okay, so it will be changed like this one. For example, it become a nasi ayam penyet. Okay, ayam penyet lah. Okay, lapar pula. So this is the deformed body. Okay, the green color is a deformed body. Okay, so the changes in size can be calculated later. Okay, so we can calculate these changes and these changes, and also these changes. Okay, so this can be calculated later. Okay, this is the changes. Let me put the delta and delta. Okay, so this delta can be calculated later. All right, so what we call this phenomena is deformation. So we call it deformation. It's deformed. Okay, so in real life, if you compress your skin here like this one, you can see the skin is deformed. Okay, for example, this piece of paper, okay, if you compress like this one, the paper will be deformed. Okay, will be changed in size. Okay, what else? A rubber band. Rubber band. If you have a rubber band, okay, you you pull the rubber band, you can see the band itself deform. Okay, change in size and shape. Okay, so this phenomena we call it deformation. And somehow, the number 3 points there, it can be highly visible. Okay, like I pulling this rubber band, it can visibly, you can see in your eyes. Okay, or somehow, sometime, practically unnoticeable. So if you have a small sample, for example, you cannot you do not um, you cannot see the deformation actually. Okay, we have to use maybe equipment to see the changes. Okay, so it can be highly visible and or practically unnoticeable. So number 4 here can occur when temperature of the body is changed. So number 4, if you have a material that can react with heat, for example, okay, the body of the material will be changed as well. Okay, when we play around with the temperature. So this is what we call it in a fourth industrial revolution. We call it 4D printing technology. So another D is the material itself can be changed according to the temperature, for example, okay, humidity, for example, like our body, of course, like our skin. Okay, if you go to the different country having a low temperature, then the skin will be squeezed like that. Okay, and if you can see here, this picture showing you the tensile test where the machine is pulling a sample there. Okay, this is the tensile. So the force is acting like this way. Okay, it's acting like this way. It's a tensile test. Okay, so when the machine is pulling the sample, and we notice that there are 3 different lines there: vertical, horizontal, and also inclination line. Okay, there. When we can see here, if you tensile, you do tensile test, you can see the line is changes as well. Okay, so this line, especially for the horizontal line here, let me change the color. But before that, let me erase this one. Okay, so let me choose the pen. Okay, for example, this line, okay, from longer, for example, this distance 10 mm, for example, when you do a compression, not compression, tensile test, the horizontal line will be squeezed. Okay, and the dimension somehow will be squeezed, maybe less than 10, for example, 7 millimeter. Okay, so this is before, this is after. Okay, before and after testing. Okay, and note there the before and after position of 3 line segment where the metal is subjected to the tension. Okay, so the line itself will be changed as well, but for this vertical line we cannot see clearly, but actually it is also changes. Okay, okay, like this one. So this is the original one. For example, the original line is 30 millimeter. When we do the tensile test, the line will become more longer. Okay, it will become maybe 40 millimeter like that. Okay, this is an example. Okay, right, and we move to the next one. Okay, so what is strain? So there are two strain. Number one is normal. Okay, number one is normal. Wait, yeah, let me check if the video is recorded or not. Okay, so okay, so it is a recording now. So let me confirm this one. So it is confirmed now. It's recorded. Okay, so the strain, normal strain. So when we talk about normal strain, this is the normal strain. Okay, it is defined as the elongation or contraction of a line segment per unit of length. Okay, so elongation, contraction. Okay, elongate like this one. Contraction when you push the material. Okay, of a line segment. So the line segment that I show you from the previous slide here, the line segment there. Okay, here the line segment. Okay, per unit length. Okay, per unit length means that we have the specific unit which is meter. Okay, is referred to a normal strain. Okay, normal strain. Okay, so average. Sorry, average. Sorry, I think the slide is not showing everything there. Let me write for you here in the presentation. Okay, the normal strain is defined as epsilon, so it should be epsilon here. Okay, epsilon average. So make sure that we calculate average. As I mentioned in the chapter 1, we are actually calculating the average because we in real life a different point at every single location, a different point at an area having different strain or stress. So, but for this case, for our lecture note, for our syllabus, we only consider average. Okay, so the average normal strain is defined as epsilon average equal to delta, okay, S prime, which is the distance, okay, minus delta S, okay, over delta S. So what is delta S prime? Delta S prime is the final length, and delta S is the initial length. Okay, so this is the equation. So normally you need to memorize this equation, this formula. Okay, so it is a changes in terms of the length. Okay, so units, for units, normal strain is a dimensionless quantity since it's a ratio of two lengths, so there is no unit for strain, but common practice to state it in terms of meter per meter. So sometimes the engineer use millimeter per millimeter, so it is similar. So it cannot be meter per millimeter, this one cannot, or millimeter per meter cannot also. Okay, the unit is the unit should be same. I mean the decimal places, the power 10 power of something is should be similar. Okay, and the number three is the epsilon is small for most engineering application. So the value for the strain is very small. It cannot go up to thousand value. Cannot, never happen. Okay, normally the range is 0 until 2. Okay, right, millimeter per millimeter, for example, or meter per meter. Okay, and so because of the small value, it is normally expressed as a micrometer per meter. Okay, micrometer per meter. Okay, right, but somehow micro, actually the good writing is like this one. Okay, so if you have the value of 10, okay, so micro should be outside from the unit lah. Okay, okay, so normally you will have this value lah, for example, so this one is become micro lah. Okay, So you can combine like this one. You can combine like this one if you have the value of 10 times 10 power of -3. Okay, so you can write like this way as well, where 10 milli per millimeter. Okay, or if you have 10, the value is 10 times 10 power of -6 millimeter per meter. So you can write micro like this one also, or 10 micron meter per meter like that. Okay, and the last one, it is also can be expressed as a percentage. Okay, for example, 0.001 meter per meter equal to 0.1%. Just multiply with 100%, you will get the percentage. So somehow in industry, if you go to industry later on for the design industry, they will normally use the percentage instead of millimeter per millimeter or meter per meter. Okay, and also it is depend on the industry as well. Okay. Okay, this is the illustration. Just want to show you how we can calculate the approximate final length of the line segment. Okay, so refer to the picture first. Okay, you have two different body. The first one is undeformed body, the second one is a deformed body. Okay, so basically undeformed body having a straight line like that from A to B. Okay, and having a distance there, which is delta S. Okay, this is the distance delta S. Okay, the original, the initial length. Okay, delta S. So once we have the external forces acting this body, for example, by putting like this way, for example, this is only example. Okay, so it will be deformed like the second image. Okay, and we do have final length, which is a delta S prime. This is the final length once we have the external forces acting on the rigid body. Okay, so this slide is showing you on how to find the delta S prime. So basically, it is a rearrangement of the initial equation here. Okay, initial equation here, where you can use this equation to find the final length. So approximately, you will get delta S prime is equal to, or approximately 1 plus sigma time with the delta S. Okay, so this one is actually a rearrangement from the initial equation where the epsilon equal to sigma S prime minus sigma S, okay, over sigma S. Not sigma, sorry, a delta, okay. Epsilon equal to delta S prime minus delta S over delta S. Okay, so the rearrangement will become like that. Okay, so the important thing that you should know is this sign. Okay, so positive epsilon indicate the line is elongate. So the line, the rubber band here, I pull the rubber band. Okay, the line elongate like this one. The sigma, sorry, the epsilon should be in positive value. Okay, so if the epsilon is negative, means that the line is contraction position. Okay, we push. Okay, this one cannot be done lah. I think the other material like this one lah. So I push this one. Okay, the string will become negative value, indicating the line is in contract position. Okay, so we move to the next one. Okay, this slide showing you on how we can relate between the stress and strain. Okay, somehow the equation is different. Okay, the equation is not same. Okay, but we can understand where the stress and normal strain can be calculated from the pre-body diagram, or from the body diagram from the body. Okay, so we look at the case by case. Okay, the first case here, if you have a BC cylinder like this, okay, we have a force acting on the BC cylinder, pulling down like that way. So this is the before, this is after. So you can see the deformed body or deformed. The deformed body having delta, which is the changes in length. Okay, and then we have the initial length. Okay, this one is the changes. This is the initial length. Okay, and of course we have the final length lah. Sorry, it should be L. It should be, sorry, I will delete this one. It should be L prime. Okay, L prime. L prime. Okay, final length. This is the final length. Okay, once you have this information, you can use the formula of the stress and normal strain to calculate those two values. So from here, we can get sigma equal to P over A equal to stress. Okay, and epsilon is equal to changes. Okay, oh, it should be not this unit, not this symbol. It should be this. Oh, sorry. Wait. I supposedly I. Okay, let me go again this way. Sorry. So let me find the pen. Okay. So it should be the changes, like that, over the initial length. Okay. So the changes here, we call it delta equal to L prime minus L, of course. Okay. So if you have this value, then the delta value, then just put the delta value in your calculation lah. Okay. And this is the first case. For the second case, it is similar actually, but different, what they call it, force value. Okay, let me erase the pen here. Okay, let me erase this one. Okay, so the changes is same, which is the delta. The final is same as well, which is L prime, sorry, A prime. It's difficult to use iPad for the teaching. That's why I don't like to have online class. Okay, so you have the final and initial, and for the second case, the difference is only the force. Okay, so it will not affect the strain because we are not using the force to calculate the strain. So the affected one is only for the sigma. Okay, and also the area is also different. So the affected one for the second case is for the sigma only. Okay, but for the epsilon is remain same as case number one. Okay, and case number three, sorry, case number three, you can see this is different in terms of the length. So this will be affecting the strain calculation. Okay, so you can see the difference is here. Okay, just apply the equation. Okay, you will get this one similar. So this one is only to show you the effects of different values. Okay. All right. So the thing is same is the stress lah. Okay. All right. And we move to the next one is in terms of the application of deformation in biomedical engineering. Maybe you are still new in this topic, in this course, okay, where maybe you do not know where to apply these fundamental things in real life after you graduate. So if you want to become an engineer, a design engineer, for example, so if you involve with many design later on, you will design something and you have to test it. Okay, so if you want to test it in terms of the mechanical properties, in terms of mechanical perspective, then you have to apply the solid mechanics courses. Okay, so this is the thing that normally I done for my design related to implant, okay, insole, prosthetic leg, orthotic leg, okay, dentures and so on. So we want to have a good design for the patient. So we design the implant, for example, and we test it using the solid mechanic fundamental knowledge, and we can see the changes there. If you can see here, model 1, model 2, model 3 is the different implant. I'm not showing everything, I'm just showing the value on the bone itself. Okay, if you can see the relative motion means that RM is a relative motion. Okay, so relative motion means that it is a deformation or motion between one point to another point. Okay, so this is the different. eh, Okay, and you can see this is the fracture sign at the tibia bone. Okay, so in real case scenario, we have to make sure that the design is stable enough to sustain the load coming from the upper body, for example, in this case. Okay, so to make sure that the fracture is stable enough. If not stable, then means that maybe other complication happen to the patient, like a second surgery, second fracture, secondary fracture, and so on. Okay, so in this case, we have to find the lowest RM, which is model number 3 lah. So we found that model number 3 or design number 3 is best. Okay, best in terms of the stability. Okay, the fracture is not moving far away each other. Okay, because the RM is low compared to other models. Okay, the second example here is the insole. You can see if you want to design insole, for example, for certain cases like cerebral palsy case or stroke patient, maybe in the future you want to design insole for the stroke patient, you have to consider the design as well. Okay, the distance, the changes distance here. Okay, okay, when you apply the load, okay, is it good enough for the denture for the stroke patient or not? And the third one is this one is badminton. I'm only showing you the bone itself, not the insole or not the mechanism on how we deal with the study. So you can see the changes here. Okay, the deformation. This one is deformation of the talus bone. So if the talus bone moving far away from its original position, maybe injury will be occur. Okay, maybe injury will be occur. So you can simulate that particular movement to ensure that there is no injury for the badminton player, for example, in this case. Okay, this is the application in biomedical engineering. All right, so we move to the example one. Okay, example one, a force acting on the grip of the lever arm shown in figure A causes the arm to rotate clockwise through an angle of theta equal to 0.002 radian as shown in figure B. Okay, figure A is the original position. Figure B is the final position. Okay, what you have to find is to determine the average normal strain developed in the wire BC. So we do have a wire BC there. Okay, you can see the line segment there is a horizontal line, and what you have to do is to find the normal strain. Okay, again, normal strain is equation epsilon equal to delta S prime minus delta S over delta S. So you can also write this way, L prime minus L over L. So delta means many changes, but for this one is only one change. That means that there is no need to put the delta. Okay, just put L prime minus L over L. Okay, so in this case, L prime, okay, you are not having L prime yet. So in this case, L prime is CB prime, okay? And the original L is CB, okay? And the original length is CB lah, okay? CB is given, CB is equal to 1 meter, enough. The unknown value is CB prime. So how to find CB prime here? So CB prime, I draw it here. Let me draw them. Let me draw. So maybe this is the CB prime. Okay, so you have to find the CB prime first. Okay, and put the CB prime into the equation, and you will get the answer. So how to find it? Okay, so this is the way. If you look at only by yourself, maybe you will not understand. So let me explain this one. Okay, so basically the angle is given there. Okay, you can see from the question the angle is delta theta equal to 0.002 radian. Okay, and if you convert this one 0.002 radian into degree, okay, you will get 0.1146 degree, showing that this value is very low. Okay, very small, so you cannot notice the changes. Okay, 0.1, even 1 degree is also difficult to see, okay, using your naked eyes. But you can imagine 0.11 is also difficult to see the changes. Okay, so once we have this information, you can see that there is small changes in terms of the angle there. Okay, we can assume, okay, we can assume this triangle, let me draw this triangle, okay, is like somehow like this one lah. So this is the theta, okay, the theta, and the theta here is a 0.1146 degree. It's very small. It is very small. Okay. In mathematics, if you learn this circle, and then you have to find s here, this is r, this is theta. Okay, so this is the equation to find s is r theta. Okay, you have to use these mathematic fundamental things. Okay, for the solid mechanics. Okay, and you have to use this equation to find the bb prime. Okay, to find the bb prime. So bb prime can be defined as s. Okay, bb prime equal to r. R is the distance 0.5, and the theta is 0.002. So you will get 0.001 meter. So it is similar like this one. Okay, once you have the bb prime, okay, this is a bb prime, so just put it into the equation. Okay, like I show it here. Okay, so you can write like this one, bb prime over cb as well. Okay, so let me write here lah to avoid confusing. So the basic things that you need to know is the equation. Okay, delta s prime of minus delta s over delta s. For this case, L prime minus L. Okay, so L prime minus L is equal to BB prime over CB. Okay, so you have this value of BB prime, so just put it into the equation and CB into the equation. You will have this answer. Okay, as simple as that. And I think the confusing is this part nah, this part. This part. So you have to, as I mentioned to you, you have to familiar with the mathematics. Okay, trigonometry, integration, differentiation, and so on. Okay, so we move to the next one, which is shear strain. Okay, so shear is another way. Normal is normal lah. N. Okay, shear is T. Tangent. Okay, so what is a shear? Let me do quickly. Shear is change in angle. Okay, because in real life situation, there are there are two different in 2D, in 2D, there are two different direction. Okay, there are two different direction. So let me draw this segment. So you have in 2D lah. Wait, let me change the color. You have this direction and you have this direction. Okay, you have this direction and you have this. For the stress, you have a normal stress. Okay, normal stress. You have a shear stress. Okay, normal stress and shear stress. Okay, tau and also sigma. Okay, but for the shear, also two direction. Wait, yeah, let me change the color. You have a two direction as well. Okay, so let me pick the middle one is the thing that you want to calculate. This is direction, this is another direction, normal and tangent. Okay, because the body can be deformed like this way or this way, right or left, right or up. Okay, so we have a tangent and also a normal. Okay, and the shear strength again change in the angle between two line segment that were perpendicular to one another refer to shear strength. So from this figure, you have A, B, and C here. So from A to B is the normal one, and of course A to C should be a tangent one, and this direction and this angle should be 90 degree lah, perpendicular. Okay, perpendicular. Right, so this is the undeformed, this is the original, this is the final deformed. Once you have the deformed body, the angle will be deformed, or not deformed, will be changed. Okay, the angle will be changed. If you can see here, this is the angle, or the change this angle from blue color to red color, blue color to the black color is changed as well. I put a delta. Okay, not delta, gamma, sorry. Okay, so the second statement here denote gamma and measured in radian. So the shear strain should be in radian value. Yeah? So the gamma here, gamma nt means that normal to tangent, okay, equal to half pi, okay, minus limit theta prime, theta prime. So this is the equation. Okay, and you have to remember the value as well. When the theta prime lower than 90 degree will be positive shear strain, and while theta prime over 90 degree should be negative shear strain. Okay, so this is the thing that you have to remember. Okay, and then okay, one more thing is that not all cases to find the shear span you have to, I mean, if you have a different cases scenario, not necessarily to use this equation, not necessarily to use this equation. So I will explain you a bit about this one later in the example too. Okay, because you have to understand the changes. For example, if you have this rectangular box, okay, and then you have the axis like this one, okay, and you have another body which is deformed body. Let me draw the axis first. Let me draw the axis first. So you have another body which is deformed, is the undeformed, is deformed. Huh. So if you apply the external load to the body, maybe, okay, I put the body like this way lah. So the body will be changed in this position. Okay, right? Okay, all right. Okay, so basically the thing is that you have to find the gamma nt. So where is the gamma nt? So if you have these changes, you can put it gamma NT like this way. NT, like that. Okay. And if you have this case, different case, like I put a different case scenario here. So the changes like this one, for example, so the gamma NT will be here. Okay. And if you have a trigonometry calculation, means that you do not need to use this equation. I think you not really understand this one because you are not experiencing the example yet. And if you go through many example during the revision and so on, you will understand it. So make sure that you do a lot of revision, a lot of exercise, discussion with your friends. Okay, because solid mechanic is not having one solid answer. The answer will be different for every single cases. Okay, it should be different. So you have to make sure that you have a lot of exercise to understand everything. Okay, I move to the next slide, which is the application of strain in biomedical engineering. Okay, so maybe you are not aware why we need to study this strain with this solid mechanic. Okay, so this is the application. So if you become an engineer later on, you will maybe lah, you will calculate the strain of the bone, okay, to see the healing process. For example, okay, if you become a researcher, researcher lah, maybe master PhD, or maybe if you join R&D department in multinational company, okay, maybe you will use this application, this knowledge to do the analysis. So you can see the bone healing process by having the strain calculation there. Okay, more strain, okay, or optimum strain will be promoting the healing process of the bone. Okay, so is a strain, okay, non-adopted RD is a different scenario case lah. So the researcher having two different treatment, they can see the different. Okay, and then maximum strength here, average strength here. Okay, so this is the thing. I'm not explaining this further because maybe this one is not yet to your standard of knowledge. If you want to go further about this one, maybe you can think about it for your FYP, final year project, or maybe master or PhD study. Okay, so we move to the example two, the last example before we end the video. Okay, so the example two is showing you on how to find the shear strain. So the plate is deformed into the dash shape as shown in the figure. If in this deformation, horizontal lines on the plate remain horizontal and do not change their length. Okay, so you have to understand the question first before you answer. So the thing is that here, this deformation horizontal line on the plate remain horizontal. Okay, the horizontal line here from A to C, okay, is remain unchanged. Okay, the changes part is only at the vertical line, AB line, AB line. Okay, so AC line will be remain as it is. Okay, and in this case, what you have to do is to calculate the average normal strain along the side AB. Okay, it is similar like example one previously. Okay, average normal strain. Okay, changes in length lah. Okay, so changes in length side B. And number two is you have to find the average shear strain in the plate relative to the x and y axis. So we have two axes, x and y. So you have to find shear strain. So I just give the clue for the second one where the shear strain should be occur at the changes what do you call it, at the changes angle. Okay, changes angle. So changes angle is here. Okay, so it should be gamma lah. So you have to find the angle here to get the gamma or to get the shear strain. So this is the gamma or shear, the changes. Okay. All right. So how to do? The first thing is that you have to find the normal strain lah. So normal strain, like in the previous example, you can use trigonometry, okay, to find the initial and final length. Okay, in this case, you will draw AB line and AB prime line. This one should be AB prime. Okay, and use the trigonometry equation. Okay, you will have a AB prime. So just make it like this dot line. Okay, you can see there. Okay, and you will get AB prime here lah, AB prime here using the trigonometry, using the Pythagoras theorem. Okay, so AB prime should be equal to square root of 250 minus 2. So this distance lah should be 248. Okay, plus 3 power of 2. So you will get 248.018 millimeter. And once you have this value, okay, then just put it into the equation. Okay, so it should be epsilon AB average, okay, should be AB average equal to AB prime, okay, minus AB. So AB prime, you got it from the Pythagoras theorem there. AB is the original one from the body, from the equation, from the question, and you will get the final answer should be negative 7.93 times 10 power of negative 3. Okay, or you can rewrite this value into this milli. Okay, but to avoid confusing, I suggest you to write this one, the circle one. I suggest you to write the circle one to avoid confusing. If you write this, the second one will be confusing many people. Okay, not even the lecturer, even the engineer later on in the industry. So it's better to provide the first answer like that. Okay, so this is the normal strain. The second one is the shear. So shear, as I mentioned to you from the previous slide, so the thing that you have to find the shear is the angle from the original line of vertical line to the deformed line of the vertical line. Okay, which is the gamma there. So from here you can calculate the gamma also from the trigonometry equation. No need to find theta prime, no need to find theta prime, and no need to use the equation that I show you early. This one, no need to use this equation because you can directly get the gamma from the picture. Okay, this is what I meant from my previous explanation just now. So some cases you no need to use the equation of the strain, I mean the shear strain. Some cases you can directly get the angle from the picture. Okay, so for this case we can get the gamma from the picture itself. Okay, where the gamma sy equal to the inverse tangent. Okay, so you have this triangle. So this one is AB prime. Okay, this one is 248. Okay, this one is 3. Okay, so sorry, so it should be inverse tangent. Okay, we want to find this gamma, right? Inverse tangent 3 over 250 minus 2. Okay, so this one is 248 lah. And the answer should be in radian. Don't forget, the answer should be in radian. If you provide angle in degree, then the answer will be wrong. Okay, the answer will be wrong. Okay, so this is the final answer. This is the final answer. Okay, all right. So enough for this example 2. So example 3 is the different scenario. Okay, so this is the tricky one. Okay, you have to find the shear strain gamma xy. So in this case, there are 4 axes: y, x prime, and y prime. So what you have to do, you have to understand the question, where is this shear strain located? So gamma xy should be xy position lah. Okay, not x prime, y prime, not like that. It should be xy position. Okay, so I give you a clue, but this one you have to think by yourself or discuss with your friend, because I don't like to give direct answer. So you have to think, where is the delta, gamma SY, where is the gamma SY located? So either this way, I make it, either this way, okay, either, or, or, or this way. So you have to think, either, okay. Okay, you have to think and discuss with your friend, where is it? Okay, so if you think, then you can understand lah. Okay, I don't like to give the direct answer. Okay, so do it by yourself, discuss with your friend, okay, and get the answer together. Also example 4, okay, example 4, okay, also I'm not discussing this one. Okay, this one you have to find both delta gamma sy and gamma s prime y prime. Okay, at point A, at point A only, at point A. So where is the delta gamma sy? Where is the gamma s prime y prime? Okay, the answer is given there. Please try by yourself. And the last one is example 5. I think this one is similar that I explained before. Okay, you have to find strain as a y at the corner A and B. So A here, B here, having different answer. Okay, the answer is there, very short, very straightforward. You can study by yourself. Okay, if you have any problem with this, tell me, inform me. If you want to discuss why we choose this length and so on, please let me know. Okay, and I think that's it from me. And hopefully you can understand the chapter 2. Okay, and this is the final final slide for the chapter 2 presentation, and thank you, and see you in the next video for the chapter 3. Okay.